So today, for part C, the first step that we need to do is balance this reaction here. The reason we need to balance this is because later we're going to be doing molar conversions, and that requires a balanced equation to be able to be correct. So this is an acidic condition because we mixed it with sulfuric acid. So I'll walk you through the steps of balancing a reaction in acidic conditions, and that will give us the information needed to be able to do molar conversions in the second part, part C. So step one is to balance non-O or H atoms. But before we do that, we need to write out our half reactions. So first one with manganese, and then we have our second one with iron. You can label them 1 and 2. So the first thing we want to do is to balance non-oxygen or hydrogen atoms, and we can do this by using coefficients. So we look up here, first half reaction, one manganese atom, they're balanced. Secondly, with our iron, one iron atom, they're balanced. Secondly, we need to balance our oxygen or hydrogen atoms. Firstly, we're going to do our oxygen atoms just by convention. So we see here that there are 4 oxygen atoms on the left side of our first half reaction, and there are none on this right side. To balance this out, we can add water molecules and add a coefficient in front of it. So we need 4 oxygen atoms on the right side of our first half reaction. So by putting a 4 leading coefficient in front of our water molecule, this will allow us to have 4 atoms of oxygen on both sides. On the second half reaction, we do not need to balance oxygen because it is already balanced. There is none. So now we need to balance our hydrogen, because we see that when we add water, we also add hydrogen atoms onto the right side of our half reaction, our first one. So 4 times 2 is 8, so there are now 8 hydrogen atoms on the right side and none on the left side. So we can do this by adding hydrogen ions, which have a charge of +1. And we can add a coefficient in front of this 2 to also balance out our half reactions. So on the left side, we know that we need to balance out 8 hydrogen atoms, so we can add a leading coefficient of 8 in front of this hydrogen ion in order to have 8 hydrogens on both sides. And we do not need to do this here again because there are no hydrogen atoms present in the second half reaction. So what we do next is we need to balance our charges. We can see that there's a charge on the MnO4, which is -1, and on the hydrogens on the left side it is 8. There are 8 single charged hydrogens, and when you add these together, this comes out to a total of a +7 charge on the left side. On the right side, we can see that the manganese has a charge of +2, and water does not have a charge, it's 0. So when you add these, this comes out to a +2 charge on the right side of this half reaction. The way to balance this is we need to add electrons. Electrons are negative, so we are going to add electrons to the side with the higher charge in order to bring it down to be equal with the side of the half reaction with a lower charge. We can find out how many electrons we do by taking the higher side, which in our case is the left side, which has a charge of 7, and subtract the lower side, which has a charge of 2. This leaves us with 5. So we know that since this is the side, the left side is the higher side in terms of charge, we need to add 5 electrons in order to bring it down to a charge of +2. And on the bottom here, we can see that the right side has more charge than the left side, so we can add 1 electron, since 3 minus 2 is 1. So we can add an electron here in order to bring them both down to a charge of 2. Now what we're going to do is we need to balance our half reactions. And what I mean by that is we need to have these electrons cancel out when we rewrite them. Right now there are more more electrons on this side, it should be 5, than there are here. So the way that we can get 5 electrons in this half reaction is by multiplying this side by 5. So we can add coefficients of 5 in front of all of our atoms or substances in this second half reaction in order to make it equal to our first half reaction. Now we see that this is a little hard to see, but there are 5 electrons here. And now that there are 5 electrons here, these can cancel out. So we don't need to factor these in when we go to rewrite. So now that this is finished, we need to rewrite our half reactions. So we can do this in green. So it will be MnO4 minus plus 8 hydrogen ions plus 5 iron plus 2. And the way that we rewrite this is on the side of the arrow on the left, we use all of the parts of the left sides of both of our half reactions. So the left side of our arrows, we look at them in both. So it would be the cutoff would be here, the cutoff would be here. So we use all of these, which just happens to be 5 iron, and then we use these. And the same goes for the right side. So now that we have rewritten our left side, we are going to also rewrite our right side. So that would become Mn plus 2 plus 4H2O plus 5Fe plus 3. And in purple, we are going to rewrite our net. This is our total ionic equation. But our net ionic equation is what is actually just reacting. And we're going to use these coefficients in the second part to determine our molar conversions. So in this case, we just want to look at what's actually reacting. So in this case, it's going to be MnO4 plus 5Fe plus 2 arrow Mn plus 2 plus 5Fe plus 3. This is our net ionic equation. This will be used in part 2 of part C. Okay, so our second step here is molar conversions. So you would have performed a titration of an MnO4 solution into a solution of water and an unknown FeSO4 solution. So the way that you are going to determine that of the amount of Fe+2 by mass is, first of all, we need to calculate how many moles of MnO4 we have, and then we will convert that into the amount of moles of Fe+2. So to begin, what we need to do is we actually need to find out what our volume of MnO4 is. So by doing that, you take your titration results of how many milliliters you used, and you will average them up, which is essentially adding your results and then dividing them by how many results you have. So in my case, it was 4. And then you will put it in, that will give you the result in milliliters. But in chemistry, we work with liters. So our volume would actually be 0.02994 liters, because mine happened to come out to 29.94 milliliters when it is rounded. So what we're going to do is we need to discover the amount of moles in our MnO, of how many moles of MnO4 we have. So this would be this number here in liters, 0.02994 liters times the molarity of our solution, which would be 0.091 moles per liter in our situation. Theoretically, it should be 0.1, but there is definitely room for error, and you should not have exactly 0.1 moles per liter. So in our case, you would use whatever you calculated for your molarity of in part B. But in my case, it happened to be 0.091. Let's fix that up. Moles per liter solution. So, doing some quick calculations off screen, this would equal 2.74 times 10 to the power of -3. This is scientific notation. If you are not using scientific notation, that is okay. That is just my personal preference. Moles. This is how many moles of MnO4 we have. So now what we want to do is we want to convert this to how many moles of iron plus 2 we have. So we can see the reason we balance this equation, we wanted to get this 5 leading coefficient of iron for a reason. We now know that since there is a 1 leading coefficient, this isn't really, we don't need to show this because that's just by convention we don't show that we have a leading coefficient of 1. But this shows us that we have a 1 to 5 ratio, molar ratio of MnO4 to Fe plus 2. So what we want to do here is we know that we have 5 times the moles of Fe plus 2 than we do MnO4. So if we want to calculate the amount of moles in our Fe plus 2, it would equal 2.74 times 10 to the power negative 3 moles, which is same as our moles of MnO4, times 5. This is our molar conversion. So this leaves us with, again, I am doing calculations off camera, because this is just stuff that you can plug into your calculator and you'll get the same results, but you just use your own data. Oh, this should be A2. And then this would be rounded in my case to 1.362 times 10 to the power of negative 2 moles. This is how many moles of iron plus 2 we have. But wait, this question asks us, they want percent composition by mass, not by moles. So now we need to convert the amount of moles of iron plus 2 we have into mass. And there's a quick way we can do that, is by determining what the molar mass of iron plus 2 is. So the molar mass of iron is 55.85 grams per mole. So we can use this to determine how many grams of iron plus 2 we have. So our mass of iron plus 2 is equal to the amount of moles we have times 55.85 grams per mole. And this comes out to 0.761 grams. So now we've discovered how many grams of Fe plus 2 we have in our solution, in our unknown solution. Just going to move this down for some more space. So now what this question wants us to determine is what is the percent composition. So the way to determine or calculate what percent composition it is we use the formula, our part, which it would be 0.761 grams, over our total, which is 4 grams, because we mass out 4 grams of our unknown iron sulfate solution. And then we are multiplying it by 100, because it is a percent calculation. So, doing the math, this comes out to 19.03. So what this number tells us is that in our solution, 19.03% of it, of our unknown iron sulfate solution, is Fe plus 2.